So we will define what is an inner measure based on our previous definition on the outer measure and relate these two measures in the context of measurability. Before we give the definition, let us provide an alternative characterization of the outer sets that our outer measures, I should say, and this will be our motivation in defining what is an inner measure. To start, let us consider a collection of subsets of X. So let C be a subset of the power set of X. And we define the following collections: C sigma and C delta. So C sigma is the collection of all countable union of elements in C. And in a similar manner, C delta would be the collection of all countable intersection of elements in C. Here, sigma, the Greek letter for S, corresponds to the French word somme, which literally means sum. So you can think of C sigma as combining, okay, the elements of the collection script C. On the other hand, delta here, which is the Greek letter for D, is the first letter for the German word Durchschnitt, and this means average. So you can think of what common or on the average elements of sets in the script C. So first, we provide some remarks by taking this AN to be just one set in C. So in other words, you have a constant sequence of elements in C. Then you have that this collection C is contained in C sigma, and in the same manner, C is also contained in C delta. Well, you can iterate these processes, but if you take, for instance, C sigma sigma, so this is the countable union of the countable union of elements in C. Well, that is basically the collection of countable unions in C. So if you have the same subscript, then you end up by removing one. So you can remove two the same indices, and you consider only one index. And of course, as I said, you can iterate this. So let's start with, say, a C sigma. Then this is contained in C sigma delta, and so on. So you can also have the countable union of the countable intersection of the countable unions. And in the case of C delta, you can take, let's say, or permute or interchange the subscripts, and you have another chain of collections. So you have an increasing sequence in this case. In general, C sigma and C delta might not be comparable. However, if let's say I have a sigma algebra, say sigma, then this sigma algebra is left invariant under this operation. So for instance, in sigma, of course, you have one inclusion. which is if you replace C here by script sigma or sigma, then the reverse inclusion follows immediately from the fact that a sigma algebra is closed by countable unions. And since it is closed under countable intersections, then you have this. Again, iterating these processes, you have the same collection. Okay. So in the case of sigma algebras, these operations make the sigma algebra unchanged. Okay. So, well, if R is a ring, so if you have a collection and R is a ring, then you can have an alternative definition for these collections, which we state in the following theorem. So if R is a ring on X, then first one, if you have an element of R sigma, then this is the case. If and only if you can find a sequence of elements in the ring such that AN increases to A. So here you have an additional property that you can take the sequence to be increasing. In an analogous manner, an element in R delta is precisely the limits of decreasing sequences in the ring. Okay, let us look at the proof. And here we will only illustrate the case of R delta, since the construction is the same as the union. So we need to prove two directions. So let us consider the easy part. So if this is the case, then A would be, so if AN increases to A, then okay, A would be the union, hence it is now in R sigma. Okay. If AN is increasing and increases to this direction follows easily from the definition of R sigma and the definition of the limit of an increasing sequence. For the other direction, if I take, let's say, an element in R, it should be a Bohr's intersection. If I have an element in R delta, then we can, let's say, write this as the intersection of B sub n's for some B sub n in R and a positive integer. Okay. So here it is not necessary that the sequence is decreasing. So let us construct a decreasing sequence that preserves the intersection. If I take, let's say, A sub n to be, let's say, the intersection of the B sub case, k from 1 to n. Okay, so you just cut off the countable intersection into a finite intersection. The index n refers to the number of sets. So if you take this, then of course, the intersection of the A sub n's is the same as the intersection of the B sub case or the B sub n's. Okay, from 1 to n or 1 to infinity. Hence, B or A sub n decreases to A. And take note that A sub n is in R since you have a ring, and the ring is closed under countable or under finite intersections. So yeah, indeed, given an element in R delta, we can write it as decreasing, as the limit of a decreasing sequence of the ring. Let us say here the case of 1, you just basically replace the union or the intersection by the union, and of course you replace the increasing sequence, no, the decreasing sequence by increasing sequence. So there's a correction here. This should be decreasing to A. Okay, so that's the proof. So in the case of the ring, which we consider in the succeeding discussions, one can replace the sequence by an increasing sequence in the case of R sigma, and a decreasing sequence in the case of R delta. Okay. So with that, let us consider, let's say, an alternative definition for the outer measure in terms of these collections. So let us consider the following theorem. So let's start with a pre-measure space. With R a ring on X. And let's say mu star the outer measure induced by your pre-measure mu. Okay, so let us just recall the definition last time. So for a subset A of X, or an element of the power set, then the outer measure of A is defined to be the infimum over all. Okay, so you start with, let's say, a covering, a countable covering of A with sets in the ring. And then you take the measure of each set and then take the sum. And with the convention that if there's no such a covering, and then we set the infimum of the empty set to be infinity. Okay, then we could write the outer measure of A as follows. So the outer measure of your set A is the infimum of the outer measures of E. So here we replace the countable covering by a single set. But then this E must be in R sigma. So loosely speaking, we replace this union here by a single set E. And because this countable union, it is natural to consider an element in R sigma. Okay. And why is that? Take note that this is in R sigma. Okay, so that's let's say a different definition for the outer measure. Okay, so let us look at the proof, and let us define the right-hand side for simplicity by, let's say, small m sub a. So something like the outer measure of a. So the idea here is to prove that the left-hand side is less than the right-hand side and vice versa. Okay, so let's start with a set containing A, say E, and E is in R sigma. Then by the monotonicity of your outer measure, this means that the outer measure of the smaller set A is less or equal to the outer measure of the larger set E. And now, taking the infimum overall such E. By this, I mean that, okay, let's change the color. This one, meaning A is a subset of E, and E is in R sigma. So the infimum there is what? So the infimum of the right-hand side is M sub A, okay, by definition, this one. So this is greater or equal to the outer measure. Okay, since M sub A is the greatest lower bound, and M star A is just a specific lower bound. So that's a one inequality. Now, to prove the other inequality, let's start with the definition of the outer measure. So in other words, you take a countable covering of A with elements centered in. So for that, you consider a sequence elements in the ring that covers A. Now, if I take, or I define this as my E, then obviously E is in R sigma. And by the definition of MA, MA is the infimum, so therefore this is less or equal to this specific outer measure, E, that covers A. Okay? And here, by applying the subadditivity or sigma subadditivity, to be precise, of your outer measure. So the outer measure of the union is less or equal to the sum of the outer measures. And by the same process, taking the inf overall such A, okay, and by this we mean that this covering A satisfies these properties. So the infimum of the right-hand side would be the outer measure of A by definition. Okay, and this is less or equal to M sub A. Okay, so here, of course, first you need to consider the case that the outer measure is finite so that you can have this covering. And in the case where this is infinite, then obviously this inequality is satisfied. So one is less than the other, and we have also the reverse inequality, and this gives us the theorem. Okay, so this is a simpler, well, definition of outer measure, you can say, but of course they're equivalent. Since, as I said, you replace the countable union by a single set, but now your single set is in R sigma, but take note that R sigma are countable union of elements in the ring. So here, the outer measure is obtained in the following way. Suppose this is your set A, and to compute the outer measure, so you can take a set larger than A, say R, say what, E, R sigma, and then you, of course, you want to take the infimum. So here, to have a smaller excess, you need to make this closer to A. So take a smaller set E that covers A. And from that, you get the outer measure. Okay, in the case of the inner measure, what we do is we take a set inside. Let's say F. And now F, okay, it's not in R sigma, but in R delta. Okay, so the idea here is somewhat, if you take the complement and R, in the case where R is an algebra, then an element in R sigma has a complement in R delta, and vice versa. Okay, so this is your F that is inside. So if you want to, let's say, have a better approximation, let's say, of your area, then you need to make this to be larger. And that motivates us in the definition of the inner measure. So the inner measure, let's say mu subscript star, okay, is defined on all subsets of X. So induced by a pre-measure, say mu on a ring R, is defined as follows. So the inner measure of A is now the supremum of outer measures of F contained in A, and F in R delta. So yes, as I said, the motivation of this definition comes from the previous theorem, where the outer measure is the infimum of outer measures of sets that contain A, but those sets must be in R sigma. So you replace the set to be inside A and the set to be in R delta. And of course, you need to take the supremum. By the monotonicity of the outer measure, you can show that the inner measure is also monotonic. It is always, okay, also less than the outer measure. Okay. Well, naturally, because for the inner measure, you get sets from the inside, and for the outer measure, you get sets from the outside of A. And the inner measure is, let's say, sigma super additive. By this, we mean that for any, let's say, subsets of X that is pairwise disjoint, the inner measure of the union is greater than or equal to the sum of the inner measures. So you can think of this as the reverse inequality for the subadditivity. But of course, we need to take the additional condition that your set is pairwise disjoint. Okay, so the proof is left for you to verify. And it is similar to the proof of the sigma additivity for the outer measure. Okay, so here, let us use this definition, let's say, to provide elements in what R sigma or R delta, or an iterate of it in relation to sets having finite outer measures. For the next theorem, let's say, with the assumptions above, in other words, you have a pre-measure space on a ring, and you have this inner measure. For any subset A of X, having, let's say, a finite outer measure, then there exist two sets. Okay? Let's say A1, this is in R delta sigma, and A2 in R sigma delta. Okay, such that A1 is contained in A, and A in turn is contained in A2, and the outer measure, let's say, of A2 is the same as the outer measure of A, and the inner measure of A is the same as the outer measure of A2. So this should be replaced, or I should say A1. So the outer measure of A1 is the same as the inner measure of A. So let me explain the idea behind this theorem, and this will give us, of course, a way on how to prove this theorem. So looking at A1, so here A1 is a subset of A. So if you take, let's say, the outer measure of A1, that is the same as the inner measure of A. And the idea here is that, of course, if you use later the definition of the inner measure, okay, so the inner measure should, or the inner measure involves sets in R delta. So the idea would be you want to take a countable union of elements in R delta. So you combine the sets from the inside in order to get this set A1. And on the other hand, this A2 here contains A, And in fact, well, up to a set of measure 0, then this will imply that, well, meaning the outer measure of A2 and A are the same. So somewhat loosely speaking, they differ less. Okay? And to get this A2 here, take note that if you want to take the outer measure, you consider a set in R sigma. And in order to get a set that will have an outer measure that is the same as A, according to this one, you need to take the intersection. Okay. So let us go into the specific details of that idea. The first step is the construction of. Let's start with A2. Since since the outer measure of A is less than infinity, meaning finite, you can always find a covering in this way, this part here. So applying also the definition of the infimum, okay, for each n, a positive integer, there exists, let's say, a set E sub n in R sigma with the following properties. So En contains A, and the outer measure of E sub n is less than a slight number greater than the infimum. So let's say 1 over n. Okay, this follows from the definition of the infimum. Because mu star of A is the greatest lower bound, then mu star A plus 1 over n must not be a lower bound. So this means that you can find a set having an outer measure less than this quantity. Now, if I take, let's say, A2, so if you take A2 to be, what's the goal? Going back to our goal, okay, we need to construct an element of R sigma delta. So I need to take the intersection in these E sub n's. And since E sub n is in R sigma, so this is in R sigma delta. Then, okay, each A is contained in E sub n, so therefore the intersection of the E sub n's still contains A. In other words, A is a subset of A2, the intersection, and by monotonicity of your outer measure, you end up with the following. So let's start with estimating the outer measure of A. Since A is a subset of A2, then this is less than or equal to the outer measure of A2. Since A2 is a subset of E sub n, take note that the intersection is independent or is smaller than any of the set involved in the intersection. So A2 is a subset of E sub n for all En. then again, monotonicity implies that this is the case. So combining the two inequalities, the outer measure of A is less than or equal to the outer measure of A2, but this is in turn less than or equal to the outer measure of En, but the outer measure of En, according to this inequality here, is less than the outer measure of A plus 1 over N. Now, if you pass to the limit N to infinity, by squeeze theorem, you get that the outer measure of A is the same as the outer measure of A2. Okay, so that's the properties of A2. So to highlight those, so A2 must be in R or sigma. It must contain A, and the outer measure of A2 is the same as A. And we have established those in this part, this, and finally this one. So that is the construction of A2. And now you have an idea how to construct A1. So instead of considering the outer measure, we consider the inner measure. So what we do is for each n, by the definition of the supremum, there exists an f sub n in R delta, wherein f sub n is a subset of A, and let's say the outer measure of f sub n is larger than the supremum, that's the inner measure, minus 1 over n. Okay, so this left-hand side will not be an upper bound anymore because mu subscript star A is the least upper bound. So in that case, you can find a number greater than that quantity. Okay, by monotonicity of mu star once again, you have that mu star of A is greater than or equal to mu star of Fn. Okay, so let us put the inequality here. And remove this. Just mentioned here by monotonicity of mu star. Okay. Then, as usual, we want to take an element in our delta sigma. So it is natural to take A1 to be the union of the f sub n's. Since f sub n is in R delta, then this must be in R delta sigma. Okay, so all of the f sub n's are inside A. So if you take the union, you combine them, it is still a subset of A. And take note that f sub n increases to A, 1, by definition. Okay. Now, take note that what, or probably we recall. Uh, Let us recall that the outer measure, when restricted to the sigma algebra generated by R, is in fact a measure. This is basically the, let's say, the Han, no, the Han-Kolmogorov extension. Okay. Now, let us emphasize here that the f sub n's and a sub 1, okay, this R sigma delta will be always contained in the sigma algebra generated by R. And one can prove that easily because the sigma R contains the ring R. And R delta sigma is basically taking the countable intersection of countable union of countable intersections of elements in the ring. So it must be in the sigma algebra generated by R. So from this, we can now apply the continuity, okay, from below. So applying continuity from below of a measure, in particular this mu star, restricted to the sigma algebra generated by the ring, you will get the following. So a fn increases to a1, so therefore the limit, or let's say mu star fn, tends to the outer measure of a1. Of course, technically speaking, if you want to emphasize the measure, you can put the restriction here. But since the restriction is the same as the outer measure for sets in the sigma algebra, then you have this equation. Okay. Now, if you look at this, if you let fn tend to infinity, you end up with the following. So if we pass n to infinity in star, okay, and we have to correct the proof. Here I want the same inner measure, but here I have an outer measure. Okay, so this is not entirely correct. So here I replace this by the inner measure and modify the justification definition of your inner measure. Take note that the inner measure of A would be the supremum of all outer measures Fn, Fn in R delta, Fn contained in A. Since Fn is a specific set satisfying these properties, then the inner measure, which is the supremum, must be larger. Okay. So the limit of this is the outer measure of A1. Okay. So if we apply again the squeeze theorem, as n goes to infinity, this goes to 0. So therefore, the outer measure of A1 is the same as the inner measure of A. And these are the required properties of your set A sub 1. Again, just to review, A1 must be in R sigma delta. A1 must be a subset of A. The outer measure of A1 must be the same as the inner measure of A. And these are, respectively, these properties. One, this one, and what is that? This A1 is a subset of A. Okay, so that ends the proof of this theorem here. Let us discuss some consequences of this theorem. So here we have not yet computed the outer measure of the difference between A2 and A1. In fact, one can extend this in such a way that the difference, or the outer measure of the difference A2 minus A1 with an appropriate A1 will have outer measure 0. Okay, and that is the next theorem that we would like to establish. So let us state precisely the following theorem. So for the assumptions, again, you have a pre-measure space on a ring R and mu star, and mu sub star, or mu star, and be the induced outer measure. Now let us take an element which is measurable in the Caratidori sense, having a finite outer measure. And you will see later the significance of this one. Then, this is only a subset of X. Then this A is measurable if and only if, so we have the following equivalence. There exist two sets, say A1, now in, well, not in R delta sigma, but in R sigma delta sigma. So now you have three operations. Okay. Countable union, uncountable intersection of countable unions. And A2 in R sigma delta, such that, okay, A1, so it's the same. A1 is contained in A, and A is in turn is contained in A2. And the outer measure of the difference between the largest set and the smallest set is 0. Okay. So for sets having a finite outer measure, measurability is equivalent in looking for two sets, A1, A2, in these collections. R sigma delta sigma and R sigma delta respectively, and the outer measure of the difference would be 0. So here, the course notes should be modified with this set. And you will see later the reason why this is the case. Of course, note that A1 and A2 belongs to the sigma algebra generated by R. Okay. Now, if this is the case, okay, you have measurability, and vice versa. So loosely speaking, we are saying that the measurability of A, okay, as long as the outer measure is finite, is the same as, well, having a larger set, say A2, and a smaller set, say A1, wherein the difference of what? A2 and A1, so this should be corrected to A1. Has an outer measure 0. So let us visualize that by, let's say, some finite set of points. Okay, so in this way, the difference is this region here. And let us highlight that part. So A2 minus A1 would be this. And here I visualize a set having outer measure 0 to be just, let's say, a finite discrete set of points. And this highlighted region is your difference. So this is A2 minus A1. And again, as I said, having an outer measure 0, just think of area, let's say, is illustrated by a set of a finite number of points. Of course, in general, a set having an outer measure 0 does not necessarily imply that your set is finite, neither countable. There are, in the case of the Lebesgue measure, for instance, there are sets having outer measure 0 that is uncountable. And an example of that is the Cantor set. But we will not go into the details of that. Okay, but here, just for the sake of illustration, the difference is illustrated by a finite number of points. Okay. So this means that A, well, roughly speaking, is almost the same as A1 and A2. Okay. Except for this, let's say, at least in this, as I said, diagram, except for a set of finite points. So this is just, of course, what, a rough idea. This is not, as I said, precise, but just to give us an intuition what is happening in this theorem. Okay, so let us look at the proof. So we need to prove the equivalence So let's start with what? 1 or the other direction. 2 implies 1. Okay. I will not repeat the assumptions here. So suppose I have an A1 in R sigma delta sigma and A2 in R sigma delta, satisfying these two properties. So if those are satisfied, so let A1 and A2 be as in 2. Okay. Then by monotonicity, the outer measure of A minus A1 is 0. So what would be A minus A1? So let us highlight that one. That would be this region here. And let us put that one. Of course, please ignore the overlaps. So this should be your A1 minus A2, or I should say A minus A1. Okay, and why is that? Of course, since A minus A1 is a subset of A2 minus A1, and the outer measure is non-negative. Okay, so this implies that the outer measure of A minus A1 is less than or equal to the outer measure of A2 minus A1, which is 0. So mu star is less than or equal to 0, but since an outer measure is always non-negative, that leads us to the conclusion that the outer measure of A minus A1 is indeed 0. Now, with this, we can write A as A1, okay, the one from the inside, okay. So this is A1 here, and A1 is, if you combine that with the difference, so this is the union of A minus A1. As we have said already, A1 is in sigma R. Okay. Now, a set having an outer measure 0 is always measurable. So this must be in sigma mu star. Hence, this is also measurable since the sigma algebra generated by R, or the elements of the sigma algebra generated by R are all measurable. And we have established this last time. Okay. So therefore, A is measurable. Again, the main idea is that I want to write A as the union of two measurable sets. You can, based on this decomposition here, you can write this as the union of the smaller set and the difference here. Okay. So it remains to establish the measurability of A minus A1, since the union of two measurable sets is again measurable. And we can establish that, I mean this one, thanks to this observation here, and the fact that sets having outer measure 0 are measurable. So that is the main idea of the proof. For the reverse direction, so we need to establish that 1 implies 2. So let's start with a measurable set. Now, by the previous theorem, we can find, let's say, a sub 2 in our sigma delta, such that A is contained in A2. And at the same time, the outer measure of A2 is equal to the outer measure of A1, or A. Yeah. So let us take the difference so that this is 0. Now, take note that the outer measure of A minus A1, A2 minus A, would be the difference. Okay. And why is that? Again, since now here we will use the fact that the outer measure restricted to the measurable sets is a measure. And this is the Caratodori extension of your pre-measure space. And what else? A2 is in sigma R. Therefore, it is measurable as well as A, by assumption. And of course, you can do this provided that the outer measure of A is finite. Okay. This is again to avoid the possibility of having the ambiguous difference of two infinities. Okay. So we need to make sure that this must be finite. Okay. So that's A2 minus A. And let us repeat the figure there. So let me copy this one. Okay, so here we need to let us just remove the colors if it is possible. Oh, it's not possible to remove only the colors. Okay, so let us repeat the figure. So you have A, and let us concentrate on A2. At this point, and take the difference and this one. So this is A2 minus A. This has an outer measure 0. Okay, so again, just for the sake of illustration, let us emphasize or say that the difference consists only of a finite set of points. Okay, so the problem here is we want to take a set inside A, wherein the difference is also as outer measure 0. Well, here, going back to the previous theorem, if it is possible to show that this is the case, then that would be A1 here would be enough. But we will prove, we don't have this yet, okay? We will prove this later on a special case. In other words, when is it possible that the outer measure of A is the same as its inner measure? That is the case, provided that your pre-measure space is finite. In other words, the measure of X or the pre-measure of X is finite, and that requires that you have a pre-measure on an algebra, okay? But here we only have a ring, so we do not have that particular information yet. So to proceed, so that's why we need a different set here. It's not the A1 from the previous theorem. But what we do, this should be corrected to A. What we would like to do is to apply the previous theorem to the set, to this difference, A2 minus A. This means that I can find a set A3 in our sigma delta, okay, such that, so this is in sigma delta, so it must be larger than the set. And the outer measure of what? The outer measure of A3 is the same as the outer measure of the difference A2 minus A, so this should be A. So if these two are the same, then this is equal to 0. Okay, now since this is finite, in fact, this is equal to 0. Okay. Yes, that is the case. Where's that? Here. Okay. So therefore, this is also equal to 0. And you can say that this is, I think that would be enough. Okay. And let us write this in a better way. So the outer measure of A3 is the same as the outer measure of A2 minus A minus A. This is equal to 0. So here we have a set larger than this blue region here. And let us say that would be this green part here. This, let's say, annular region. So this should be A3. And just to emphasize that set, let us highlight the region. Okay, so this will be your A3. It will contain it contains the region blue, and blue, take note, is the difference A2 minus A1. Okay. Now, if we take this set, we are interested in this set. and also this one. First, let us consider this set here. So this is basically A2, but then A3 is removed. And this is, as I said, A2 minus A3. Okay. So to do that, A2 minus A3. Take note that this is so A2 minus A3 will now be smaller than A2 minus A2 minus A. Okay, and why is that? Take note from here, A3 is larger, so if you subtract A3 to A2, that would be smaller than subtracting this set difference A2 minus A in A2. So subtracting a larger set to the same set would give you a smaller set. And you can see that this is what? Since A2 is a subset, or since A2 contains A, this is basically A. Okay. Now let us define, claim that this is now our desired A1. A1 is equal to A2 minus A3. So this is our A1 here. And we verify that this is in fact contained in A. And you can immediately see in this figure. Okay. So what are the properties that we would like to show? So we claim that so this is A1. Okay. So we need to show that A1 is in R sigma delta sigma, and that the outer measure of A2 minus A1 is equal to 0. Okay, so let us look at what the proof of this theorem, and let us prove that the outer measure of the difference is 0. Okay, so let us prove the second item. So the outer measure of A2 minus A1. So this is the outer measure of A2. Okay, since A1 is also in R sigma delta sigma, okay, so assuming that this is true at the moment, you can perform this computation, okay, and plugging in the definition of A1, that's A2 minus A3, okay, and what would be this case? So this is the same as So instead of doing this, I think there's a different way, and in fact a simpler way. A2 minus A1, this is equal to A2 minus A2 minus A3. Okay, be careful on this one. A3 is not a subset of A2. So what we need is to subtract this. So subtracting A3 and A2 is the same as subtracting A3 intersection A2 with A2. And you can prove this easily by algebra. Now that this is a subset of that, this is equal to A2 intersection A3. And this is a subset of A3. Hence, applying the monotonicity of the outer measure, and the fact that the outer measure of A3 is 0, which has been emphasized here, then we have the second claim. So that is the outer measure of A2 minus A1, which is less than or equal to 0. But again, the outer measure is non-negative. Hence, this is equal to 0. Okay. So this inequality or this equality here, okay, can be recognized in the following way. That would be this region here. A2 and then you subtract A1, you get this part, which is basically the intersection of A2 and A3. So that would, yes, let's just put it here. This part here will be your A2 minus A3, which is basically, or I should say A2 minus A1, and this is basically A2 intersection A3. So the intersection of this and A2. But take note, A3 is only until here. In other words, if you take the intersection of this region and this region here, the common part would be this portion here. Okay. So that's the visualization of this equation here. Aha, we still need to prove this one. But this is basically just applying the definition of your sigma delta set. So to see that, take note by construction A2 and A3 belong to our sigma delta. We have what? So we can write this as the what? Intersection of the countable union of elements, let's say what? In the ring. Let's say E to JK or IJ, I from 1 to infinity, J from 1 to infinity. And similarly for A3, so this is what? Let us use a different index, K from 1 to infinity. The intersection of the union A3 KL. All of these sets A to IJ and A3KL belongs to R. So if you compute the difference, so take note that A is equal to A2 minus A3. And where is that? This one here. And of course, by definition, this is A2 intersection A3 complement. And if you apply, let's say, first the definition of A2 or the representation of A2. So this is the countable intersection of the unions A2IJ intersection A3 complement. So distributive law. And if I use this and apply De Morgan's law, so this would be okay, let's change the grouping symbol here. So apply De Morgan's law, you will have the following. So the operation will be flipped in that case. So this will be now 1 to infinity. This is what A3KL complement. Now you consider what the distributive property, and you end up with the following. So this is what I from 1 to infinity, and then the union. Here we now combine the two indices J and K, and then the intersection L from 1 to infinity of A2IJ intersection A3KL complement, but that is basically this one here, the difference. Okay, and since we have a ring, this is now in R. Okay, therefore A1 is an element of, okay, so let's start with this. This is delta. Okay, and this is sigma, and this is delta. Okay, so again, it is the countable intersection of the countable union of the countable intersection. And I think we need to correct the statement. So this is not correct. This is this should be replaced by delta sigma delta. Okay, yes, that should be the case. So please interchange and also in this one, okay? Replace this by delta sigma delta. So in other words, the difference of two elements of this collection belongs to this one. Simply applying the properties of sets and the fact that, or using De Morgan's law. Okay, properties of sets, distributive law, commutative law, associative laws, and the De Morgan's law. And that ends the proof of the theorem. Okay. So for the last theorem of this lecture, as I said, we now connect measurability in the context of outer and inner measures. But to do that, we need an algebra. And the pre-measure space is finite. So you have X, A mu, a finite pre-measure space on an algebra A. Then the following are equivalent. Here we do not need the assumption that the outer measure of A is finite because we already have a finite pre-measure space. Okay. Or I think we still, yes, we don't need that assumption. So A would be measurable if and only if the outer measure is the same as the inner measure. So let us look quickly at the proof of this theorem here. Let A2. First, of course, note that the outer measure of A is less than or equal to the outer measure of X. But since X is in the algebra and the outer measure coincides with the pre-measure on the algebra, we have this. For any A, a subset of X. Okay, and then let us take the proof of this direction here. 1 implies 2. So suppose A is measurable we need to prove that the outer measure is the same as the inner measure. Okay, and for this, we only need to show that the inner measure is larger than or equal to the outer measure. Because the inner measure is always less than or equal to the outer measure. So we only need to prove this one. So for this, let us consider the complement and take a set E containing the complement of A. And this E is in R sigma. Okay, we should say A sigma because we now have the algebra A. Then the complement of E is contained in A, and because A is an algebra, you can immediately see that this is in A delta. We just apply the definition of being an element in A sigma, that is a countable union of elements in the algebra. If you take the complement, you apply the Morgan's law, you will now have a countable intersection. And since you have an algebra, the complements will be in A. Okay. Now, if we apply the definition of the inner measure, so the inner measure of A is the supremum of outer measures of sets in A delta that is a subset of A. since the complement to B is a particular example of that, so here we have this inequality. And this can be written as the outer measure of X minus the outer measure of E. And you can do this since your pre-measure is finite, and hence by monotonicity, it implies that your outer measure is also finite. Okay. And E is measurable. Okay, since again, let us repeat that one. This is a measure. And E, and hence E complement is in the is measurable. So in fact, it is in the sigma algebra generated by A. Okay. We rearrange this inequality. So the outer measure of E is greater than U of X minus the inner measure of A. Since E was an arbitrary set in A sigma that contains the complement, taking the inf over all such E. And by this, we mean that E contains the complement and E is in A sigma. The infimum of the right-hand side would be the outer measure of the complement. And of course, again, using the fact that A is measurable, yes, that is the assumption here. The outer measure of the complement is the measure of X minus the outer measure of A. And we should have here greater or equal. Therefore, you can cancel now these two. Multiply by -1 both sides, you end up with the fact that the outer measure of A is less than or equal to the inner measure. And since the reverse inequality is always true, then we have a 2. Okay. In other words, the equality of outer and inner measures. And finally, for the reverse inclusion, since A has a finite outer measure, let A1 and A2 be such that this is in R delta sigma, A2 in R sigma delta. So this is the one that we established before. 2. This is not the correct direction. This must be the one that we need to establish. So going back here, have this, and the outer measure of A1 is equal to the inner measure of A. Then, if you take the outer measure of A2 minus A1, well, this is equal to the outer measure, or the difference of the outer measures. Again, this comes from the fact that A2 and A1 are measurable, and the outer measure of A1 is finite. And this is equal to, according to this, and this is now 0. Well, we can repeat the proof as before. This implies that A is measurable. Well, let us look at the previous theorem. And where is that? Okay. So if you have this, okay, and A1 and A2 are measurable, then you have this part here. Okay, so you can repeat the proof of the one provided here to prove the measurability of A. And we will not repeat the process because they are just the same. So to summarize this theorem, for a finite pre-measure space on an algebra, that is, for a finite pre-measure space on an algebra, measurability is equivalent to the equality of the outer and inner measures. And let us emphasize here, where did we apply the assumptions, or where did we use the assumptions? The finiteness was utilized in this argument, okay, to know that the outer measure of any set would be finite. And for the algebra, we applied, where's that? This one. Okay. So the complement of elements in A sigma must be in A delta in order to relate the outer and inner measures. And so this is it for outer and inner measures. In the next lecture, we will discuss complete measure spaces.